Okay, I welcome you to week 4 online facilitation of PHY 205, Introduction to Space Physics. Today, we are going to look at Unit 3, which is Thermodynamics of Module 2. Okay, so let's introduce this. Thermodynamics is a field of physics that describes and correlates the physical properties of macroscopic systems of matter and energy. I hope you remember the definition of matter. Matter is anything that has weight and what? Occupy space. While energy is the ability or capacity of a physical system to perform work. Okay? The principles of thermodynamics are of fundamental importance to all branches of science and engineering. A central concept of thermodynamics is that of macroscopic system, defined as geometrically isolable piece of matter in coexistence with an infinite, unperturbable environment. Okay, what is the objective of this unit? At the end of this unit, you are expected to be able to, 1, define thermodynamics. 2, to state the gas laws. 3, to be able to derive the ideal gas equation. And then 4, should be able to differentiate between the ideal gas equation of state for a specific gas using mass, that is M, and specific gas constant R from the ideal gas equation for any ideal gas using moles and the universal gas constant R star. And then you should also be able to show that the virtual temperature, TV, as T subscript V, is given by T subscript V, which is equivalent to T all over 1 minus E over P into 1 minus epsilon, then close the bracket. Okay? Then you should also be able to define geopotential. What is geopotential? And then you should also be able to state the laws of thermodynamics. Then you should be able to explain adiabatic processes. So let's start with gas laws. Equations of state, that is ideal gas law, and then Boyce and Charles law. Now, the equation of state, the ideal gas equation is given by PV equals to mRT, where P is pressure and V is volume. M is mass, and then R is the specific gas constant, and then T is temperature. Okay. Now, if it is the case of universal gas constant, and then the gas using moles, the equation becomes PV is equals to N R star T. Okay. Then Boyle's law states that if only temperature T and mass M are held constant, are kept constant, volume is inversely proportional to pressure. Let me take that again. Boyle's law states that at constant temperature and mass, volume is inversely proportional to pressure. Okay, you should be able to state that. Then let's look at Charles' law. Charles' law. The Charles law is divided into two. We have Charles law 1 and Charles law 2. Charles law 1 states that at constant pressure and mass, the volume is proportional to temperature. Let me take that again. Charles law 1 states that at constant pressure and mass, volume is proportional to temperature. Then Charles law 2 states that at constant volume and mass, pressure is proportional to temperature. In this case, pressure is directly proportional to temperature. Hope you understand the difference. The first law, Charles law, pressure and mass are held constant. And then that's when we have volume is proportional to temperature. Then Charles law 2 states that at constant volume and mass, in this case, pressure is proportional to temperature. Okay? And virtual temperature and equations of state for dry and moist air is equals to PD, that is pressure, subscript D, that's in terms of dry air, is equals to rho RDT. Rho means density. R is the gas constant, and for dry air, and then T is equation. Okay, so is the equation of state for dry air. The virtual temperature TV is a fictitious temperature, allowing expression of the equation of state with moisture present using overall density, rho, RD, and TV, which is virtual temperature, given by the equation as shown. Okay. Now, so overall density is sum of dry air density component plus water vapor component. And TV, virtual temperature, is defined as TV is equals to T all over 1 minus 0.378 E over P. Then pressure becomes rho, that's density, multiplied by gas constant for dry air, RD, and then the virtual temperature. Thus, the total pressure is given by gas law for dry air using the virtual temperature. We can see that the gas law for dry air is given by P, pressure, is equals to RD equals to density, rho RD TV, as I said. Note that since E over P is less than 1, TV is greater than or equals to T, and rho is equals to P over RD TV. Now, if you make from the equation of the gas law for dry air, if you make rho the subject of the formula, you divide both sides by RDTV, and then you have rho equals to P all over RDTV. Then moist air has lower density and is therefore lighter than dry air. Hydrostatic equation, geopotential, which is phi of Z, that is in terms of height, and height Z. And then hypsometric equation. Let's look at that. For equilibrium state, non-convecting conditions, in which downward gravitational force is nearly balanced by pressure. The hydrostatic equation, given the rate of change of pressure with density and local gravity G, is given by del P over del Z equals to minus rho G in bracket phi and Z, close bracket. Phi is geopotential, Z is height. Okay. Then the geopotential can be defined as work required to raise 1 kilogram to geometric height Z, And then the unit of geopotential is joules per kilogram. Joules per kilogram. Thus, it is a function of height and the non-constant local gravity. Geopotential height using globally average standard acceleration GO and geopotential is defined as Z is equals to Z over G naught, small g. Note that the definition uses constant G naught, which is equals to what? 9.8 meter per second square. And then define exactly rather than varying G. G is not varied. Geopotential thickness of a layer between pressure levels is given as Z2 minus Z1, that's initial geopotential height, minus the final geopotential height Z2 minus initial geopotential height 1 equals to RD over G naught. Then integral of P2 to P1, TV, which is virtual temperature, dP over P. Hydrostatic equation using geopotential height Z and G naught is given by del P over del Z, which is equal to minus the density multiplied by the local gravity. And then, or you take the inverse of that, still the same. So hypsometric equation, HE, is the potential thickness of a layer between two pressures using mean virtual temperature, TV, and is given by Z2 minus Z1, RD equals to RD over G naught, then mean of virtual temperature, then the natural log of P1 over P2. The hypsometric equation is used for mapping pressure surfaces and layer thicknesses, which serves as a forecasting tool. So note that as the mean of virtual temperature increases, the layer becomes thicker, and the thickness of a layer is greater where air is warmer. Let me take that again. Thickness of a layer is greater where air is warmer. Okay. Now, first law of thermodynamics. First law of thermodynamics. This expression of the first law of thermodynamics expresses the conservation of energy. We said the energy is neither created nor destroyed, but is converted from one form to the other. For an ideal gas, working substance of mass M, fully enclosed in an insulated cylindrical container, bounded at one end by a movable piston and at the other end with a fixed wall. When heat, the Q in joules, is added to the gas, the heat may increase the internal energy of the gas, the U, also in joules, and do work, dW, on or by the environment in joules. In this case, interacting with the piston. The equation is given as the Q, which is heat, is equal minus dW, which is the work done, is equals to du, which is the internal energy of the gas. These variables change independent of the manner in which the system moves between the two states. Okay, now specific heat, that is the mass specific heat capacity of a gas at constant volume, is defined as CV is equals to the change in heat over the change in temperature when volume is kept constant. And the unit is joules per Kelvin per kilogram. The first law of thermodynamics is alternatively for alpha, which is specific volume. Alpha is specific volume and is given by the Q is equals to the U, which is the heat, plus internal heat, plus P, the A. Now, first law for ideal gas, expressed per unit mass, is given by the Q is equals to C, a specific heat, multiplied by the change in temperature, plus pressure, the A. Dry adiabatic process and potential temperature. Okay. Adiabatic processes are processes for which the Q is equals to 0. That's the heat. Heat is equals to 0. No heat is added or removed in the system when dry parcels of air are lifted rapidly so that there is no condensation or evaporation and no radiation. Then the process is dry adiabatic. The process is dry adiabatic. If I ask you to define dry adiabatic, you should be able to do that. Note also that until condensation forms at the moist unsaturated parcels that are lifted also follow a dry adiabatic, and for them the process is also dry adiabatic. For dry adiabatic conditions, we have pressure multiplied by specific volume. That's pressure P alpha. Pressure multiplied by what? Specific volume is equals to gas constant, the T. That's R the T. The dry adiabatic lapse rate in P coordinates is given by the ratio of D dt over the P is equals to alpha, which is specific volume, over Cp. And this is far greater than 0. Now, I'm giving you a self-assessment exercise. You are to define geopotential and write the mathematical expression defining all terms. I said what? Define geopotential and write the mathematical expression defining all terms. I expect you to do that. Conclusion. In this unit, we have learned that PV is equals to MRT is the ideal gas equation. PV equals to MRT is the ideal gas equation. While PV equals to N, small n, R star T is the ideal gas equation or equation of state for any ideal gas using moles and the universal gas constant. Also, that the adiabatic processes are processes for which the Q, that's heat, is equals to 0. No heat is added or removed. Summary now. In this unit, we learned that Boyle's law states that if only temperature and mass are held constant, volume is inversely proportional to pressure. Then Charles law 1, the first Charles law states that if only pressure and mass are held constant, the volume is directly proportional to temperature. Then Charles law 2 states that if only V, that's the volume, and mass are held constant, the pressure is directly proportional to the temperature. So we will stop here today. We are going to stop here today, and I expect you to do all the self-assessment exercise I've given you. And in 2 weeks or 3 weeks' time, we shall organize a special session for question and answer. So I'll see you next week. Wish you all the best, and make sure you read your course materials. Best of luck. Thank you.